Okay, so I want you to picture something for me. You've got this document in front of you. Maybe it's a huge transcript or just a raw data dump from a web crawl.
Mm-hmm.
And it has no formatting, no chapters, no headers, no paragraph breaks, just a relentless, unbroken stream of words.
The dreaded wall of text, the kind of thing that makes your eyes just glaze over in about 3 seconds.
Exactly. And your job is to take, I don't know, a red pen and draw a line exactly where one topic ends and the next one begins.
It sounds simple enough.
It sounds simple, right? You just look for where the story changes. But when you try to teach a machine to do that, to automate it, it turns out to be one of the trickiest problems in natural language processing.
It really is. It's sort of the invisible problem. We take for granted that articles have headlines and our reports have sections.
Right.
But for search engines, for summarization tools, for, data retrieval, figuring out those boundaries, what we call text segmentation, is the engine that makes everything else work.
And today, we are going deep on a paper that proposes a really, really novel way to solve this, titled Improving Text Segmentation with Non-Systematic Semantic Relation.
A bit of a mouthful.
It's a dense title, yeah, but it's from the Japan Advanced Institute of Science and Technology. And the core idea is, well, it's surprisingly intuitive. It's about teaching computers to stop just reading words and start understanding context.
Not just context in a sentence, but context in the world.
Exactly, or at least a Wikipedia-sized chunk of the world.
Which is a pretty good substitute.
So before we get into the heavy math, and we are going to talk about treating text like a digital image, which is just wild, let's look at the status quo.
Okay.
If I'm a standard, off-the-shelf algorithm trying to chop up a document, how am I doing it?
Well, historically, you're relying on something called lexical cohesion. This is really the bread and butter of text segmentation.
Well, cohesion.
Yeah, it's based on the work of Halliday and Hassan, and it goes all the way back to the 70s. The theory is pretty straightforward. A segment of text hangs together because the words are, well, glued by relationships.
And I'm guessing the strongest glue is just repetition.
Right. It's called reiteration. If you're writing a paragraph about solar energy, you're going to keep using the word solar or sun or maybe panel. A computer can easily track that. It just counts the frequency of matching words between sentences. If sentence A has solar and sentence B has solar, the computer assumes the topic is continuing.
So it's basically just a sophisticated Control F.
In a way, yeah. It also handles simple synonyms or superordinates like knowing that peach and fruit are related.
Okay.
These are what we call systematic semantic relations. You can find them in a thesaurus. They are static. A peach is always a fruit. That relationship doesn't change.
But, and this has to be the problem, the paper highlights, human language isn't static. We don't just talk in dictionary definitions. We talk in themes.
Precisely. And that's where the standard algorithms just fall apart. They fail when the vocabulary shifts, but the topic stays the same.
Right.
If I switch from talking about the Hubble telescope to talking about astronomers and orbit, I haven't changed the topic. I'm still talking about space exploration. But if I'm just counting word matches, Hubble and astronomers share 0 letters.
To a basic algorithm, that looks like a topic break.
Exactly. It gets confused.
So this brings us to the non-systematic part of the paper's title. This is the gap they're trying to fill.
Right. A non-systematic semantic relation connects words that don't have a rigid dictionary-defined relationship, but are strongly linked by context.
The paper gives a great example for this. The words paper, contribution, review.
Okay, let's break that down. If I just say the word paper, what comes to mind?
A blank sheet for a printer or a newspaper.
Sure. And if I say contribution, what do you think?
A charity donation, maybe?
Right. But now, if I put them all together, paper, contribution, and review, suddenly the meaning just collapses into a single specific context.
An academic conference.
An academic conference.
Paper now means a research submission. Review means peer review.
Exactly. But you will not find review listed as a synonym for paper in any dictionary. They are related only because of the situation they appear in.
That's a non-systematic relation.
That's it. It's invisible to a thesaurus, but it's completely obvious to a human who knows how conferences work.
So the challenge is, how do we give a computer that kind of street smarts? How do we teach it that translation, word, and meaning are a squad, even if they aren't synonyms?
Well, the authors mention that previous attempts using things like WordNet failed.
And why that?
WordNet is a database of lexical relations. It's great for Izzy's relationships, like a dog is a mammal, but it's terrible at these loose contextual associations. Plus, it's mostly nouns and it's manually built. It just doesn't scale well to the messy reality of language.
So they needed something new.
They needed a model that could learn these connections from scratch just by observing how language is used in the wild.
Which brings us to the heavy artillery, topic modeling.
Ah.
Specifically, latent dirichlet allocation, or LDA.
Yeah, and I know. Don't tune out at the acronym.
Right.
LDA is actually, it's fascinating. Think of it this way. LDA assumes that every document is a mixture of hidden topics, and every topic is a mixture of words.
Okay, but doesn't know what the topics are, right? Doesn't know politics or sports.
It has no idea. It just knows that ball, score, and game tend to hang out together mathematically.
So it's looking for clusters of co-occurrence across a massive data set.
Yes, it's all probabilistic. It says, if I see the word galaxy, there is a high probability I'm in topic 86. If I see star, there is also a high probability I'm in topic 86. So even if galaxy and star never appear in the same sentence, they're linked through this hidden topic 86.
But to learn those probabilities, you need a ton of data. You can't just run this on the single document you're trying to segment. That would be, well, circular.
Exactly. You need a universal training ground. You need to show the computer the world. So the researchers used Wikipedia.
And not just a few articles. They used the entire Wikipedia dump. 3 million articles. 6 million distinct words.
This is so crucial. Wikipedia is what they call topically balanced. It covers history, science, pop culture, geography, everything.
So by running LDA on all of Wikipedia, the model learns the company that words keep across almost every conceivable human subject.
Exactly.
There's a specific example in the paper that really crystallized this for me. They analyze a text called Stargazers.
Right. It's a standard text for this kind of testing.
So the text is describing the Hubble Space Telescope. And I'm looking at the words the model picked out. In one segment, we have Hubble, telescopes, astronomers, planet, and spacecraft.
Okay, now stop there for a second. Imagine you're that old school algorithm.
Okay.
Hubble and astronomers, no shared words. Planet and spacecraft, no shared words.
Right. To it, they're unrelated. But the Wikipedia-trained LDA model looks at this and assigns them all to topic 680.
Exactly. It says, hey, I've read 3 million articles, and in the grand scheme of things, Hubble and astronomer belong to the same mathematical bucket.
And then, just a few sentences later, the text switches to words like orbiting, star, and galaxy. And the model assigns those to topic 86.
Which is distinct, but you can tell it's highly related. The computer is no longer looking at letters, it's looking at ideas.
It sees a block of topic 680, followed by a block of topic 86.
And it can track that thematic flow even if the author stops repeating the word telescope.
Okay, so they have this massive Wikipedia-brained topic model. But how do they actually use that to slice up a specific document? This is where the paper gets really creative. They propose a system called JSegT.
Right, and it's a hybrid system.
Hybrid.
Yeah, they didn't want to throw away the old methods completely. Repetition is still a strong signal. If I say peach 5 times, that's useful info.
Sure.
So JSegT calculates similarity between sentences using 2 measures.
Okay, so measure 1 is the classic TF-IDF, looking for shared words.
Right, the old school way. And measure 2 is the topic-based similarity using that LDA model. They use a metric called Jensen-Shannon divergence.
That sounds like a plot point in a sci-fi thriller. We have to stop the Jensen-Shannon divergence.
It does, but in simple terms, it just measures the distance between 2 probability clouds.
Meaning?
Well, if sentence A is 90% topic 680 and sentence B is 85% topic 680, the divergence is low. They are close in topic space even if they share 0 words.
So they combine these 2 scores, word overlap and topic overlap, to get a total similarity score for every pair of sentences in the document.
Right.
And this is where the visualization comes in. This is the part I really want to unpack because it just flips the whole problem on its head. They create something called a dot plot.
Yes. This is a vital shift in perspective. Imagine a graph. On the x-axis, you list every sentence in the document, say 1 through 100.
Okay.
On the y-axis, you list the exact same sentences 1 through 100.
So it's a grid.
A grid. Now, take sentence 1 and sentence 1. Obviously, they're identical, so their similarity is 100%. You put a bright white dot in that square.
Makes sense. And sentence 1 versus sentence 2.
If they are similar, you put a light gray dot. If they are totally different, a black dot.
So if I have a paragraph of 10 sentences all talking about the Hubble telescope, they all going to be similar to each other.
Exactly. Sentence 1 matches sentence 2 and 3 and 4. Sentence 2 matches 1 and 3 and 4, and so on. What you end up with is a bright square block of light right along the diagonal line of the grid.
And that square is the topic.
That square is the topic, and when the topic changes...
The similarity drops.
Yeah.
The box ends. You get a dark region. Then a new bright box starts for the next topic.
You've got it.
So the problem of text segmentation just became a problem of finding the squares on the grid.
You've turned a linguistic problem into an image processing problem. But there is a catch.
Of course there is.
Real text is messy. The grid isn't perfect. It's fuzzy. There are random bright dots where there shouldn't be. Maybe a random word connects two unrelated sentences. The image is noisy.
It looks like a low-resolution, grainy photo.
Exactly. And this is where the researchers pulled a tool from a completely different field. They used anisotropic diffusion.
Okay, hold on. I know diffusion generally means things spreading out, but anisotropic, what's that?
Think of it as smart smoothing. If you just blurred the whole image, you'd lose the sharp edges of the squares. You wouldn't know where the topic ended.
Got it.
Anisotropic diffusion is a filter used in image processing, like in Photoshop or MRI analysis, that smooths out the noise inside a region, but stops when it hits a sharp edge.
So it looks at that pixelated, grainy similarity matrix and says, these gray dots inside the square, let's make them solid white. But this sharp drop-off at the edge, keep that sharp.
Ideally, yes. It sharpens the boundaries between the topics. It clarifies the structure. It turns a fuzzy suggestion of a topic into a really distinct block.
That is incredibly clever, using visual algorithms to clean up semantic noise.
It allows them to see the structure of the discourse much more clearly. Once they have this sharpened graph, they use a minimum cut algorithm.
Okay.
They just look for the point along the diagonal where the connection is weakest, where the cut costs the least in terms of similarity. And that's where they drop the guillotine and say, segment ends here.
So to recap, we have a Wikipedia-trained brain, converted into a visual matrix, sharpened by image filters, and sliced by graph theory. It sounds robust, but does it actually work? Or is it just over-engineered?
That's the big question. And to find out, they put JSEG-T into the ring against the reigning champions. They used the Choi dataset.
Which is a Frankentext.
It is exactly a Frankentext.
Okay.
Choi took the brown corpus, a standard collection of English text, and randomly chopped out segments. Then he glued 10 different segments together to create a new artificial document.
So it's a jumbled mess of topics, and the computer has to figure out where the glue marks are.
Right. And because we built it, we know the ground truth. We know exactly where the cuts should be. They compared JSEG against systems like C99, TextSeg, and MinCutSeg. These are the standard benchmarks in the field.
And the metrics they use are PK and window diff. Can we clarify those? Because PK sounds like a video game stat.
It's simpler than it sounds. PK is the probability of error. Imagine you pick two sentences at random from the document. The metric asks, does the computer correctly know if these two sentences are in the same segment or different segments?
So a lower score is better. You want a low probability of being wrong.
Exactly. Low PK means high accuracy.
And the results?
JSEG-T achieved the lowest error rates across the board.
Across the board.
Yeah. It significantly outperformed the standard MinCutSeg.
And remember, MinCutSeg uses the same cutting strategy.
That's the critical comparison. Both systems use the same cutting math. The only difference was that JSEG-T had that Wikipedia-based topic model mixed in.
So the secret sauce was the topic model.
It proves that the improvement didn't come from the math of the cut. It came from the knowledge of the world, the non-systematic relations, the fact that it knew Hubble and astronomer were friends.
Exactly. The other models were flying blind on context. JSEG-T had a map.
And interestingly, it was robust even when the segments were really short. Even if a topic only lasted 3 sentences, JSEG-T could usually spot it.
Which is impressive because short segments don't give you much time to repeat words. You have to rely entirely on that immediate context.
It validates the whole premise. To understand the structure of a text, you need to understand the relationships between the concepts, not just the letters and the words.
So zooming out a bit, we've built this better mousetrap for text segmentation. Why does this matter to, the person listening right now? They aren't running NLP benchmarks in their spare time.
No, but they are using the internet every day. Think about Google. When you search for best battery for a 2015 sedan, do you want the search engine to throw a 50-page mechanics manual at you?
Definitely not. No. I want the paragraph that talks about the battery.
That is text segmentation. Better segmentation means search engines can index specific passages, not just whole pages. It means when you ask a smart speaker a question, it can extract the precise answer from a long article.
It's the difference between here is a book And here's the answer.
It's also crucial for automatic summarization. If I want an AI to summarize a meeting transcript, it first needs to know where the discussion about budget ended and the discussion about hiring began.
Right.
If it blurs those together, the summary is useless.
So this is really the infrastructure for the next generation of how we interact with knowledge. We're moving away from document retrieval to information retrieval.
Exactly. And it shows that to get there, we have to treat language as something fluid and interconnected, not just a bag of words.
I just love the interdisciplinary nature of this solution. They didn't just stay in the linguistics lane. They grabbed probability theory, they grabbed computer vision techniques.
It's a great reminder that sometimes the solution to a problem in field A is sitting on a shelf in field B. Who would have thought that an algorithm designed to denoise photographs would be the key to organizing text?
It's reading between the lines by looking at the pixels.
That's a great way to put it.
So here's a thought to leave you with. We talked about how the computer learned that Hubble and astronomer are connected, not because a dictionary told it so, but because it saw them hanging out together in the probability cloud of Wikipedia.
Right. It found a hidden pattern.
So if a computer can find these hidden non-systematic connections just by crunching the math on how we talk, what other connections are out there? What other concepts are effectively synonyms in our collective subconscious, linked by how we use them, even if we don't realize it?
That is a provocative thought. We might be revealing more about how our minds structure the world than we realize, just in the patterns of our co-occurrences.
Mathematical telepathy. I like it. Thanks for diving deep with us today.
Always a pleasure.
See you next time.